まずはじめに、一般社団法人情報通信技術委員会専務理事、岩田秀之様によるご講演です。それではお願いいたします。The first speaker will be Chief Executive Officer and Senior Vice President Hideyuki Iwata, the Telecommunication Technologies Committee. Mr. Iwata, please.
Okay. Hello, everybody. I am Iwata from TTC, a standard developing organization in Japan, a leader of Autonomy Working Group in Beyond 5G Promotion Consortium. Today, I'd like to report the activity of the Autonomy Working Group. First, I'd like to talk about the Autonomy Working Group with discussing. It is held joint with TTC's Autonomous Network ad hoc group, where the experts regulatory exchange opinions, and including sharing Autonomous Network, ITU, a focus group on Autonomous Network. A non-member of TTC wishing to join the Autonomy Working Group. Next Autonomy Working Group be held separately after TTC Autonomous Network ad hoc group meeting. Next, I'd like to talk about technical landscape related to autonomy. The chart on the left shows use case architecture and trust contribution to ITU-T focus group autonomous network by the country and regions. Contributions to the use case from the EU and India are significant, and from China to everything. The graph on the right shows the number of the participant companies in the TM Forum catalyst by country, by under region, and many companies from EU and China are participating. Participating from US companies is second only to both countries. Japan lead key position at ITU-T focus group on autonomous network, where lead the architecture discussion on autonomous network. We believe that product deployment and active deployment of these technologies in real networks will be required in the future. The following table is from my report to the International Committee in Beyond 5G Promotion Consortium in June. This shows, indicates whether or not the 11 management items of autonomous network consider 3GPP, ETI, ZSM, TM Forum, and Japan. Next, we introduce the activity, the ITU-T AI ML 5G challenge as a related our activities. This will be the third time this year. KDDI Rising will provide problem statement for this Japan round. TTC for the seminar November 11 to present by the winner teams the two problem statements selected the Japan round next week. So if you are interested, please join us. The number of participation from Japan is decreasing, so we'd like to invite interested company and university next years. Finally, following my presentation, Japanese company KDDI and NEC will introduce on their their initiative on autonomy. Thank you very much.
岩田様、ありがとうございました。Thank you, Mr. Iwata. 続きまして、株式会社 KDDI 総合研究所 KDDI 株式会社大谷智博様によるご講演です。それではお願いいたします。The next speaker will be Tomohiro Otani, KDDI Research Incorporated, KDDI Corporation. Please, Mr. Otani.
Thank you very much for your introduction. So, following Iwata-san's introductory talk, I will talk about network operation automation by using AI/ML technology from a more technical perspective. So this is the example of network operations along with human beings and network operation systems, IT systems. We would like to replace human operation. Human operator usually do a lot of things indicated here, but for some reason we would like to replace human beings by computer programming for autonomous networks. So we conducted government-funded research projects thanks to MIC. We have investigated the AI-empowered end-to-end operational architecture, having design, deploy operations functionalities for very reliable telecommunication services. We would like to AI-enable more optimized operation, and as well as we would like to have AI-enable more efficient operations. Kuroda-san will indicate the planning, deploying phase, so he will touch upon that later. And I will focus on operation and maintenance part, how we get the result by AI/ML technologies. So this is a very summarized result which we have received, we have achieved during the project. Good estimation results in data pre-processing, the amount of data. As indicated on the right side, you can see the performance of AI accuracy is improved as the number of data is increased. And also, the left-hand side shows the pre-processing performance, pre-processing data improvement. So by using pre-processing functionality, we will improve the estimation result. So this slide indicates good insight for how we apply AI. End-to-end system design is really a key for high performance of AI. So this is very important things. And Iwata-san touched upon a little bit TM Forum Catalyst project. This was maybe 2 or 3 years ago, and we have indicated our project result during TM Forum. We could not receive any award at the time, but we have indicated the presence of Japanese consortium in that event. So this is the example. And now we focus on from NFV environment to cloud-native networking function environment. This was also funded by MIC. So we really thank MIC's support for this project. And we again apply AI technology to even cloud-native networking functions with NEC, NICT, and ourselves. So NEC part will be also explained by Kuroda-san later, so I will touch upon KDI part. And in this case, we deeply into the data from Linux OS level, and we can get the good AI performance by introducing such low-level data information. And lastly, in terms of ITU, the consortium contributed two contributions of a document, and also we have already presented data format standardization activity in eBPF and Cloud Native Telco Day, hosted by Linux Foundations. And Iwata-san also touched upon AI ML in 5G challenge events. This year also we provided one problem statement to that event, and currently 21 parties entries, but we are not sure how many parties will actually submit their results, so we are waiting for their submissions for review. So in conclusion, I indicated AI-enabled network operation automation is key for new era beyond 5G era. We are continuously working for envisioning autonomous technologies. Thank you very much.
大谷様、ありがとうございました。Thank you very much, Mr. 大谷。続きまして、日本電機株式会社主任研究員黒田孝之様によるご講演です。それではよろしくお願いいたします。The next speaker will be Takayuki Kuroda, Principal Researcher, NEC Corporation. Please, Mr. Kuroda.
Thank you very much for introduction. Preliminary, Iwata-san and Otani-san presented about the introducing talk. I will focus on presenting about the research and development activity of our company, especially about automated system design technology for autonomous network. Since my today's presentation is about network autonomy, let me start from introducing about the trend of autonomous network research. TM Forum separate the area of network management into these three layers: business layer, service layer, and resource layer. Business layer is about users' businesses, and the requirement for ICT services are obtained from this layer. And the resource layer is about management of ICT resources. And the service layer is about the combination of ICT resources that is configured to satisfy the requirement. And when any change of requirement or any trouble to provide the resources happen, the configuration in the service layer should be reorganized to keep the situation where the resources satisfy the requirement, and to keep providing the end-to-end service. The service operation is basically composed of these four steps: monitoring, analysis, planning, and execution. And our target to automate is in the planning phase. So why we do this research is this is a very important challenge to autonomous network, to achieve autonomous network. The automation of execution is, in other words, automation based on specific instructions. Here, the user needs to instruct very specific things, for example, specific configuration or specific workflow. This is very costful, and specific instruction is not robust to changes. On the other hand, the practical form of user's requirement is more abstract. For example, he needs VPC services that can be used by 100 people at the same time. So there is a semantic gap. So we need a technology to bridge the gap between them and realize automation that can decide specific instruction by itself. Our contribution to this problem is automated system design technology. Our technology translates users' abstract requirement to specific system configuration. For example, this is 5G network requirement hosted on AWS platform with an orchestrator for the platform, and that is used by the tenant. In addition to that, it has some non-functional requirement regarding performance and resource separation. Our technology translates it into such specific configuration. Our technology is a kind of multi-purpose combinatorial optimization problem solver that is composed of such process, design generator, and design selector. By adjusting the requirement, it can generate a variety of specific configurations, for example, for high performance or for low latency, and so on. So as conclusion, we are inventing automated system design technology to achieve autonomous network. For future work, we will enhance this technology, especially in designing speed and flexibility. And we will apply this technology to autonomous network, and we continue to contribute to international standard based on this technology. Now we are looking for POC partners, so if you are interested in this technology, please contact me. That's all. Thank you.
黒田様、ありがとうございました。Thank you very much, Mr. Kuroda. 以上、岩田様、大谷様、黒田様によるご講演でございました。Once again, thank you for Mr. Iwata, Mr. Owatani, and Mr. Kuroda for the presentation. それではこれより国立研究開発法人情報通信研究機構電磁波研究所電磁波標準研究センター研究センター長花戸優子様によるご講演を行います。どうぞよろしくお願いいたします。The next speaker will be Yuka Hanado, Electromagnetic Standards Research Center, National Institute of Information and Communications Technology. Director General, Radio Research Institute. Please, Mr. Hanado. Ms. Hanado, excuse me.
Thank you, Chairman. I'm Yuko Hanado at NICT. I would like to talk about the space-time synchronization technology for the future. And this is the outline of my talk, and there are 4 subtitles as follows. Let's start, The first one is space-time synchronization for practical use in society. The second one is what environment does space synchronization require? The third one is toward the space-time synchronization platform in future. The last one is current development and toward the standardization. Then let's start from the first one. Before the main talk, I would mention about what is the space-time synchronization. Space-time synchronization is a state where the internal clock of devices is synchronized and the position of devices is mutually recognized in the local area. This technique itself is necessary in various situations, for example, in construction of international standards, contribution in the academic field, and social implementation. And this time, let's consider from the perspective of how to proceed it for practical use in society. Then let's start from the question, why is space-time synchronization required? One great effect is to improve communication efficiency, and another is on precise localization. From the 5G era, communication terminals will be expanded to drones, robots, and connected cars, and more. For such flexible moving devices in free space, precise localization are surely required. For that, GNSS positioning is widely used so far. However, the precision of GNSS positioning largely depends on the communication environment. Poor environment will degrade the measurement accuracy. Therefore, it will be necessary to develop a platform that can synchronize time more accurately, efficiently, and robustly. Then, let's move on the second subtitle, what environment does space-time synchronization require? One solution would be to distribute devices with high precision clocks and create an environment where they can complement each other. This image gives us some insight and tips, but we should consider about some problems in actual utilization. Specifically, some confusion would be caused by the fact that this device mesh network includes communication nodes with different mobilities and applications in a growing diversity. Then let's think about the mobility organization of a little more. To get an image of further mobility, future mobility, we picked up application examples of robotic drones and aerial drones. This is a map that classifies use cases according to the usage environment and the need for cooperative control between communication nodes. Then, the utilization of drones in the suburbs, unmanned factories, drone delivery and transportation in urban areas will fit like this. To meet with such various use cases efficiently, multi-layered control platform is desirable. Here, in the most basic layer 1, simple control is enough, and the attention point is mainly development of time server on prime network hub. The more complicated communication and the more coordinated operation is required, the more delicate and advanced device control is required. For example, in urban areas, highly assisted GNSS system would be required. For example, multiplex receiving system at the base stations, beacon stations were considered for high positioning accuracy. In more advanced applications, it is necessary to grasp the posture and position of the device itself by calculating a 3D image by AI processing for multiple device data. For such higher services, genius control integrated with the edge servers is required. In that case, AI processing and VRXL main contents in 5G or 6G age consume CPU power. However, the computing power of user handsets have the limitation in cooling and battery power. Solving the problem requires advanced edge server processing that works closely with the handset. Time synchronization technology is essential for super distributed processing on edge servers. To meet such advanced demands, we need a network that properly incorporates multiple layers of time control, rather than relying solely on GNSS. This platform will consist of basements that supply time and location information universally, edge server closest to users, and cooperative mobile clocks on user devices. Around the world, the importance of robust system for time and localization is recognized again. Here, two examples in the US government neighborhood are shown. The one mentions about the news that the Department of Homeland Security, DHS, has designated positioning, navigation, and timing services a national critical function. And the other mentions about the comment of NIST, the National Institute of Standards and Technology, which says that the nation should bolster research and development of systems that distribute accurate time via fiber optic cable and radio. Both promote the awareness to the importance of the basement. On the other hand, big companies, Google and Meta, accelerate to enhance the cloud and edge servers. Google has developed Google Spanner since 2012 in the system. Instead of Lamport clock, all servers are linked with standard time using GNSS and atomic clocks. And Meta is leading the project to open source the robot servers. And as a further possibility, new autonomous local platform based on cooperative mobile clocks could be realized by space-time synchronization techniques. Basic idea is as follows. By sharing mutual time difference among the adjacent devices, and advanced clock time can be constructed as a local reference time. This cluster time scale is autonomous, robust, and flexible. Calibration is easy by accessing the basement time platform. Developing the space-time synchronization techniques will realize this idea. The core techniques that make up the space-time synchronization include the atomic clocks as actual frequency sources, highly precise time and frequency transfer, and the generation and dissemination of standard time scale. NICT has established these technologies as a national research institute and contributes to the global and national standard time for many years. Based on these potentials, NICT also started to develop 3 new researches, CLIFS, YY, and cluster clock system, are the core technologies of space-time synchronization in the B5G era. CLIFS is chip-level integrated frequency standard, which is developing a low-cost mass production method for chip-sized atomic clocks that can be mounted on mobile devices. So far, we have achieved simplification and low height design through the development of a reflection type gas cell and lock-in up-free single-loop system. Wireless two-way time comparison YY will achieve the precise time synchronization and distance measurement in real time between the mobile receivers. By improving the prototype modules, such excellent performance has been confirmed as the latest performance. Cluster clock algorithm generates a stable and robust reference time scale by synthesizing multiple clocks flexibly linked within a local network. In theoretical approach, for example, such the topocentric analysis is going. NICT is also working on the communities of standardization to make them aware of the importance of this technology. Low latency and high reliability is an important keyword in 5G, which were mentioned in 2014 as a keyword in the ITUR future technology trend toward IMT 2020. The next FTT toward IMT 2030, in other words, in 60, has been almost completed in WP5D, where we can read keyword space-time synchronization, which key technologies indicates CLIFS, YY, and cluster clock. And this is a summary, so that's all my talk. Thank you very much for kind your attention.
花田様、ありがとうございました。国立研究開発法人情報通信研究機構電磁波研究所電磁波標準研究センター研究センター長の花戸優子様によるご講演でございました。Thank you very much for Ms. Yuko Hanado, the Director General of Radio Research Institute, Electromagnetic Standards Research Center, National Institute of Information and Communication Technology. 続きまして、エリクソンジャパン株式会社主幹研究員村井秀志様によるご講演でございます。それでは村井様、よろしくお願いいたします。The next speaker will be Hideshi Murai, Master Researcher of Ericsson Japan. Please, Mr. Murai.
エリクソンジャパンの村井でございます。本日は発表の機会をいただきまして誠にありがとうございます。本日は Beyond 5G のケーパビリティと主要技術と題しまして 弊社のビューをご紹介させていただきます。まず2030年頃の、社会のイメージですけれども、弊社でもやはりサイバーワールド、フィジカルワールドが結合するというふうに考えております。そしてこのバックボーンを支えるものが 6G であろうというふうに考えております。で、6G のプラットフォームですけれども、アプリケーションやニーズとプラットフォームの関係は、アプリケーションとかニーズがリクエストを出したものをプラットフォームがサービスとして提供するといった形のインタラクションを起こすような感じで考えております。そうした場合に 6G のプラットフォームに必要とされるケーパビリティ、能力はどんなものがあるかというのをまとめたのがこちらのスライドになります。こちらのスライドでは、真ん中のリングのところが 5G でのケーパビリティとしても考えられてきたものを 6G でさらに拡張するといったものです。例えばデータレートとかがありますけれども、よく言われるのはピークデータレートですけれども、私どもはそれもさることながらアチーバブルデータレートですね、特定のシナリオにおいて一体ユーザーがどれぐらいのスループットを享受できるのか、そういった観点も非常に必要であるというふうに考えております。レーテンシーについてはさらに短くするっていうのもあるんですけれども、その一方で一体どれぐらいの遅延時間が予測できるのかといった機能も必要であるというふうに考えております。下の部分のネットワークのエネルギーパフォーマンスは 5G の時でも持続可能性とかグリーンといった関係でよく議論されてはいたんですけれども、昨今の世界情勢で今エネルギーコストがすごく高くなっております。そうしますとこのエネルギーの効率自身が6G のコストにも関わってくるということで、私どもは最近よく注目しております。外側のリングにありますのが 6G のネットワークが目指す新しい領域としてのケーパビリティを挙げております。セキュリティやプライバシー、それからデバイスの多様性、ネットワークセンシング、それから展開の柔軟性、それから信頼できるコンピューティング、それからサービスの汎用性、それからサービスの可用性と、それから復元性、こういったあたりのケーパビリティが 6G に必要になってくるというふうに考えております。そして、真ん中のところはコストにペイするもの、それから持続可能なものということで、真ん中のリング、外側のリングのケーパビリティがすべて満たせるといった場合でもコストがペイしなかったり持続可能でないとするとシステムとしては成り立たないので、こういったところを常に頭に置きながら開発を進めていくべきであるというふうに考えております。こちらの方はそういったケーパビリティを支えるテクノロジーとしてどんなものがあるかというのを世界のいろんなところの6G のコミュニティでディスカッションされているものをリストアップさせていただいたものです。私どもはこのリストアップしたものはまだ不完全だと考えておりまして、中には確かに 6G を支えるテクノロジーだよねっていうのが明らかなものもありますが、その一方で2030年のタイムフレームの中で本当に商用サービスとして実現できるのかとか、あるいはコストのペイができるのかとか、あるいは技術そのものが本当に有効なのかといった点も含めて精査が必要だというふうに考えているものもあります。以下のスライドでは弊社が主要技術と考える技術とその取り組みの一部をご紹介させていただきたいと思います。まずはじめに 6G のスペクトルですけれども、5G までで定義されてきた、あるいは使用しているスペクトル帯が青い部分になっております。それに 6G ではさらに緑色の部分ですね、7から 24GHz とそれからサブテラヘルツと呼ばれている100から 300GHz あたりを新たに開拓するものであろうというふうに考えております。そして既存の青いスペクトルの部分ですけれども、特にサブ6から下の方はカバレッジに非常に重要な周波数帯であると考えておりますので、6G でも使うことを考えております。ただここには 5G のユーザーもおりますので、5G とスペクトルをシェアする 関係になることから、スペクトルのコンパチビリティというのが非常に重要になってくるというふうに考えております。真ん中の方、7から 24GHz なんですけれども、こちらの方はまず下側の方ですね、7から 15GHz あたりに注目して開発を進めていきたいというふうに考えております。サブテラヘルツの方は周波数が高いので用途がかなり制約されるとは予想されますが、そういった中でこのポテンシャルを最大限に引き出せる使い方はどんなものであるかとか、どんなサービスが提供できるかという観点から開発をしていきたいというふうに考えております。こちらの方はサブテラヘルツの電波測定を検討したものを示しております。弊社のインドアのどういうんですかね、インドアの施設で、オープンエリアとそれから会議室があるところ、右下の方に写真がありますけれども、こういったところと右上の写真の赤丸の TX というところがバルコニー上でちょっと高めのところから、下の方に電波を放射して受信電解を測定しております。そして左側のグラフは、受信電解の測定値なんですけれども、こちらから自由空間損の電波損を弾いたその上に生じるエクセスロスというものを、確率分布関数で評価したものです。で、使用した周波数は、ミリ波帯である28ギガとか58ギガに加えて140ギガヘルツの周波数を使用しております。それで、赤いグラフのところがオープンエリアで、いわゆるラインノブサイトですね、見通し内のところでの結果ですけれども、これを見ますと、28GHz、58GHz、140GHz の間で大体似たような特性になっているので、振る舞い的にはそんなに変わりはないというふうに考えております。その一方で、会議室のあるところですね、右側のグラフになりますけれども、会議室のあるところでの、エクセスロスというものを見てみますと、28GHz 帯のロスに比べて、58GHz、140GHz はさらに損失が大きくなっているということが確認できました。ドアを開いた状態で見ると、その損失は5、6デシベルの増大なんですけれども、これ、ドアを閉めてしまいますと、14デシベル程度、かなり大きな損失が加わるということが確認できました。そして次が、ゼロエネルギーデバイスです。で、これは、ハーベスティングというものがあって、周囲の温度差とか振動とか光からエネルギーを、取り出して、それをそれでデバイスを駆動しようというものです。デバイスをそんな形で駆動しますので、バッテリーの交換とかバッテリーのチャージは不要になります。そして、これらはアセットトラッカーズという資産とか、それから荷物にタグをつけてそれをトラッキングするようなものとか、たくさんのところに展開するセンサーなどに使えるデバイスであるというふうに考えております。4G、5G で LTM とかナローバンド IoT、あるいは NR のレッドキャップといったものが検討されてきましたけれども、これらに対してエネルギー消費はもう格段に小さくて、そしてケーパビリティも格段に小さくなるということなので、これは LTM とかナローバンド IoT に比べて次のワンステップというよりは全くの別物であるというふうに考えております。そのような電力的に厳しい環境下ですので、物理層的にはどんな波形が考えられるか、どんな送受信のデバイスの不完全性について配慮しなければいけないかといった検討とか、あるいはモビリティとかセキュリティをどうやってマネージしていくのかといった観点から技術検討を進めております。次が、究極のパフォーマンスとカバレッジに対してです。で、これらの回としましては、弊社は新しいネットワークトポロジーがあるというふうに考えております。この新しいネットワークトポロジーとしては3つございまして、1つはマルチポイントの接続性、それからマルチホップの接続性、それから衛星コンポーネントによる保管の3つがあるというふうに考えております。マルチポイントの接続性につきましては、次のスライドでご説明させていただくとしまして、マルチホップの接続性については、インテグレーテッドアクセスバックホールというものがございますけれども、 これと似たようなもので、端末がリレーを介したり、あるいはそういったものが車とか、飛行体に、搭載されて、ユーザーはそういった、アクセスバックホールを介して、基地局に接続されるといったような形態を考えております。それからアンテナによるすみません、衛星による補完というのは、地上のセルラーネットワークがカバーできないところを衛星で 5G のサービスを提供するといったものです。こちらの方はマルチポイントのコネクティビティの説明のスライドになります。いわゆる分散マイモ、ディストリビューティッドマイモというものですけれども、右下の図を見ていただきますと、これは電力での評価ではありますが、マイモのたくさんの素子を中央部に集中させた場合と、右側のようにその素子をいくつかに分けてサービスエリア全体に散らばせて配置させたものになります。そうすると右側の方は左側に比べて格段に高い電解というのはないんですけれども、サービスエリア全体にほぼ一様な電解を提供することができるということと、あとミリ波とかサブテラヘルツになりますと、この受信点の間に何か障害物があると、そこで信号はブロックされるんですけれども、たくさんのノードが分散されていると、あるノードからの信号がブロックされたとしても、他の信号からの通信を供給することができるということで、堅牢なネットワークが構成できるというふうに考えております。でもう少し具体的なイメージを示しているのが上の図になります。たくさんのノード、マイモを持っているノードが密に連携しておりまして、端末は複数のノードと同時に接続することが可能になるような能力を与え、その結果によってレイヤー1のモビリティも可能になるというような形のものを考えております。で、究極の分散マイモとして弊社はレディオストライプというものを考えております。これはフィルム上の上にアンテナプロセッシングユニットというものと、アンテナ素子を含むプロセッシングユニットというものと、それからバックホールや電源供給線というものをプリントで、搭載しまして、その、フィルム上のものをさらに一次元的に接続していくといったもので、それがベースバンド処理をする CPU につながるといったような代物で、右の写真の上の赤い点々点のような形で展開することを考えております。あるいはこれのアンテナプロセッシングユニットを一次元的ではなくて二次元的にパネルに近いような配置をすることによりまして、右下の図のようにインドアの中でパネルのようなものを壁とか天井に置くことによりまして、いろんな障害物があるところでも高い周波数を使って安定的に高速な伝送を提供することができるといった観点から、検討を進めております。さらにこちらの方は、通信とセンシングの、結合といったものです。要するにセンシングの機能を通信に、インテグレートする、統合するといったもので、通信のスペクトルとインフラを、もう一度再利用するといったものなので、導入には非常にコストがかからないということと、インフラの方はたくさんのノードが密に連携しているので、センシングでそのベネフィットを、十分に享受できるといった代物です。で、レーダーのように、物体の反射で検知することもできますし、ノード間での天候によって雨が降っていたら信号が減衰するということも検知できるというような形になります。で、こちらは最後のスライドですけれども、世界中の、国がイニシアチブを取っている 6G のもの、イニシアチブとか、リージョンでイニシアチブを取っているものなどのリストを示しております。左上の方がグローバルな組織、左下がアメリカのもの、真ん中がヨーロッパ、ちょっと右側にインドがあり、中国があり、コリアがあり、日本があるというような形になっております。以上で説明を終わらせていただきます。ありがとうございました。
村井様、ありがとうございました。エリクソンジャパン株式会社主幹研究員村井秀久様によるご講演を頂戴いたしました。Thank you, Mr. Murai, Master Researcher of Ericsson Japan. それではこの後のご案内をさせていただきます。続きまして、富士通株式会社未来社会&テクノロジー本部チームディレクター、グローバル富士通ディスティングイッシュエンジニア、佐久本和則様によるご講演を頂戴いたします。それではよろしくお願いいたします。The next speaker will be Kazunori Sakamoto, Team Director of Future Society and Technology Unit, Fujitsu Limited, Global Fujitsu Distinguished Engineer. Please, Mr. Sakamoto.
Thank you, everyone, for your 15 minutes. Oh, sorry about that. Today, I'd like to talk about Fujitsu's initiatives to future ICT infrastructure. But first, just a little bit about myself. We are Fujitsu. Our purpose is make the world more sustainable by building trust in society through innovation. So, who am I? My name is Kazunori Sakamoto. My purpose is make dreams into shape by technology. I'm working for 60 Research now, and I'm certified as a Global Fujitsu Distinguished Engineer for network. So, what does future digital society in 6C era look like? Let's take a look. We believe 6G will resolve the social issues fundamentally and create a more enriched society. I'd like to talk an example you can see in the right bottom that future digital society enable smart living and work by monitoring and controlling the real world at well-being service. Health monitoring digitizes the person's conditions and activities in physical space. Data can be shared in the digital space, then it enables automatically scheduling telehealth appointments, for example. If they need to see a doctor, a vehicle is automatically dispatched by mobility service. Like this, future digital society enrich our lives, linking. The point is the linkage, linking among a variety of vertical services based on digital and physical space collaboration. So, what is required to realize this society? We focus on 5 key technologies, such as computing, network, AI, data and security, and converging technologies. There are fundamental technologies for Fujitsu's Uvance, that is our new global business brand, delivering a digital transformation portfolio. we integrate these 5 key technologies into 6G as well. Then, now what is the future ICT infrastructure architecture look like? We are designing the disaggregated and distributed architecture that 6G orchestrate everything. Now, our ICT infrastructure is very centralized, and users like smartphone are distributed geographically, but the data generated on smartphone is moved to central cloud. That data is processed there, so ICT applications are also centralized. Network gives us just connectivity. In 6G era, end users will be more distributed and more diverged. IoT sensor is one of the examples. That devices are not only on ground we can live, but also in desert, on the sea, in the sky, in the space. In such situation, is it good to move all data to central cloud? We say no. Some data is stay on end users. Some are moved to central cloud, and others are moved to edge. Data is distributed to satisfy its usage efficiently. Same time, hardware and software resources are disaggregated granularly for efficient use. These resources are distributed same as data. In this disaggregated and distributed architecture, network is not only connectivity. 6G orchestrates everything. To realize this architecture, we are working on developing the next generation ICT infrastructure. So what are we doing for this? Dive into our Fujitsu's efforts towards 6G. We are working globally to realize disaggregated ICT infrastructure for 6G in several ways. First, vision. We published a white paper about 6G network and technologies in this February. Have you read it already? You can find it on our Fujitsu website. A second, research and development. Third, open communities. Let's start with our R&D activities. To resolve social issues and make rich user experiences, we have researched its requirements and input them into R&D. From bottom, we have been developing open networks and green technologies. We have terahertz wireless, photoelectric fusion devices, next generation processor named Monaca, and disaggregated architecture design. Top of that, we are developing the intelligent orchestration. It orchestrates software components such as cloud-native services and also hardware components, as I mentioned. Next, how about our activities on open communities? We are contributing to several open communities, developing and promoting disaggregated ICT infrastructure with global partners. For example, in North America, Next Year Alliance. In Japan, Beyond 5G Promotion Consortium. in Global, ION Global Forum, and LFH. I'd like to talk in each later, but a little bit about Beyond 5G Promotion Consortium. We are contributing to write white paper there. Thank you for your kind cooperation here. Well, let's begin with NextG Alliance. We are promoting disaggregated ICT infrastructure to 6G in NextG Alliance. What is NextG Alliance? It's an initiative to advance North American wireless technology leadership over the next decade. It means 6G. NextG Alliance set 6 audacious goals toward the 6G world. We join as a contributing member. We focus on research of distributed cloud and communication systems. That is one of the NextG Alliance audacious goals. I'd like to talk it a little bit more detail. We start to research technologies for 6G distributed cloud with global partners in NextG Alliance. At this moment, we focused on 2 research items. One is optimizing disaggregated and distributed resources to satisfy end-to-end QoE. Other is intelligent orchestration for disaggregated and distributed resources. As I mentioned, all resources are disaggregated and widely distributed. Key point, we think, is orchestration to provide sufficient end-to-end QoE. Okay, move on to ION Global Forum. We are accelerating to build ecosystems and disaggregated ICT architecture in ION Global Forum. ION Global Forum is creating next-generation communication and infrastructure technologies, aiming to realize ION concept. It's studying architecture and driving park, including disaggregated computing technologies. We join as a board of directors. We accelerate to study and promote disaggregated technology in ION Global Forum. Lastly, let's go to LFH. We are developing core technologies, business models, and services in edge computing area utilizing LFH community. LFH established an open interoperable framework for edge computing in Linux Foundation. We join as a governing board. We are not only governing the whole community, but also leading the technology as a technical advisory council member. We are leading 3 blueprints in Acrylino. I would like to summarize. We are working globally to realize disaggregated ICT infrastructure for 6G in several ways: vision, R&D, and open communities. We Fujitsu develop innovative network architecture globally and contribute to future digital society through technology leadership. Thank you very much.
坂本様、ありがとうございました。Thank you very much, Mr. Sakamoto.